Welcome dear students, we are on the CEC curriculum lecture and we are in the series of electronic circuit and we are discussing the various components used in the electronic circuit. In the today's lecture we discuss about the rheostat, and this rheostat used to control the current flowing in the circuit by adjusting the resistance. So, how it is different from the potentiometer, that we will discuss. Now, a potentiometer different from the rheostat. What are the differences between the potentiometer or rheostat, we can say. A potentiometer is an instrument or component in the electronic circuit that is used to compare or measure the potential difference, while the rheostat is known as a variable resistor and is used to control the current or varying the resistance of a circuit. Next, the potentiometer controls the voltage, but the rheostat controls the current. This is the difference between the potentiometer and the rheostat. Potentiometer is a resistor with a 3-terminal and the sliding contact with an adjustable voltage divider. But here a rheostat is a variable resistor with the 2 terminals. A potentiometer is composed of resistive elements such as graphite, resistance wire, cement and carbon particles. But here the rheostat composed of the various type of material such as fluid, metal ribbons and the carbon discs. Potentiometer has a low power and is used for the audio gadgets, television manipulators and as a transducers. But here the rheostat is used as a high power electronic and appliances such as the mixer, fans and the motors. So, these circuit potentiometers connected in the parallel, the rheostat connected in the series with the circuit, and the potentiometer can be used as a rheostat, but the rheostat cannot be used as a potentiometer. A potentiometer can divide the voltage, rheostat can not divide the voltage. So, these are the basic difference between the rheostat and the potentiometer. You see on the screen that this is a potentiometer and this is a rheostat. So, how does a rheostat control the current in the circuit, that we will discuss. In order to change the current in a circuit, its applied voltage or its resistance should change. When we change the current, then applied voltage or the resistance should change as the Ohm's law. So, rheostat function for changing the circuit current happens by changing the resistance of the circuit. So, increasing the resistance leads to the decrease in the current of the circuit, and you need to connect to increase the current, and you should decrease the resistance in the circuit. If we want to increase the current, then we decrease the resistance in a circuit, so that we can control the flow of the current in a circuit through the rheostat. Now different factors affect the resistance is the length also, as we discussed in the earlier lecture, length, type and the area of cross section for a rheostat. That also these factors are also affect the resistance and affect the flow of the current. For the rheostat, this factor is the length. The after mentioned contact moves in the rheostat is the item that is used for changing the length, resulting in the change in the resistance, therefore in the current. And we are having the track path, the shape of the track path depending upon the type of rheostat we use. Does a rheostat reduce the voltage? Another question always come in the mind, that rheostat function is to change the current. So, when it is placed across a voltage source, there would be a fixed voltage across the rheostat. So, voltage will not change. With the increase of the resistance, the current decreases. As we know that V is equal to IR in the basic electrical engineering circuit, where the voltage source is fixed. The two factors should change to affect the voltage. The rheostat are used to change the current and the voltage is fixed. It should change the resistance to affect the current, and this process also affects the voltage. So we can say that the voltage can also be controlled by the rheostat, since the two items that affect the voltage changes via the rheostat. Right, now another component which is also used in the electronic circuit, we will discuss some more components which are used in the electronic circuit. One is important component is the varistors. Yeah, this, what is this varistor? Varistor is a voltage dependent resistor. You see, these are the varistors. Varistor are the voltage dependent resistor, that is also called the VDR. The resistance of the varistors is variable and depends on the voltage applied. Now the word is composed of the two words, variable resistor, then is varistors, and the varistor, their resistance decreases when the voltage increases. Now these resistor depend upon the voltage. Up to now that rheostat which depend upon the rheostat depend upon the resistance and the voltage. Now here the voltage depend on the resistor, that is a varistor, and their resistance decreases when the voltage increases. In case of the excessive voltage increases, their resistance drops dramatically, and this behavior makes them suitable to protect the circuit during the voltage surges. So causes of the surge can include the lightning strikes and the electrostatic discharges, and the most common type of the VDR is the metal oxide varistor, that is MOV. So these are commonly used. Basically varistors are non-linear two element semiconductors that drop in the resistance as the voltage increases. As we increase the voltage, resistance will drop. Voltage dependent resistors are often used as a surge suppressors of the sensitive circuits. So varistor are used in a sensitive circuit. So varistor, you can see the symbol, it is depicted as a variable resistor which is dependent on the voltage. You see, we represent the varistor like this. You see, there is a arrows, and on which there is a mark which represent the varistors. So what is the construction? As it is a semiconductor devices, so crystal of the silicon carbide or the metal oxide are pressed into a ceramic material, and sintering of the material is done at a high temperature so that it get dried, and the electrical characteristics of the devices are depend on the temperature provided the atmospheric condition. We sandwich the metal oxide into a ceramic material, press into ceramic material, and the coating done, sintering done on that. And in order to have the good electrical contact, the contacts of the material are metallized with the silver or the copper wire, and then leased as the soldering to the contacts, that varistors are furnished and the coded. Nowadays, these are the most common voltage clampers. We can call it as a clampers, and can be used for a wide range of the voltage. And it is a non-linear device and absorb the destructive energy and dissipates it in the form of heat in order to prevent the system damage. Usually zinc oxide is used, and its manufacturing, that is also known as the metal oxide varistors. You see on the screen that this is a zinc oxide used for the construction of the metal oxide varistor. This is the one of the metal oxide varistor, and it is sandwich. You will see there is a ceramic layer and the epoxy shell is there. The two wire connection on the left hand side, we have wire connecting lead we have, and metallic coating electrodes are there, and the zinc oxide is sandwiched in with the ceramic, and then it is there is covered with the some material, capping will be there. Here the varistor is formed the 90% with the zinc oxide, and the rest is filler materials that forms a junction, and that connected with the two terminals. A standard silicon carbide is different from the metal oxide varistors in the way that the MOV exhibits the less leakage current and its operation speed is faster as compared to the other. Operation and characteristics of the varistor. To understand the relationship between the voltage and the resistance of the varistors exhibit the usually behavior in case of the resistance. You see on the screen here we are having the voltage versus resistance. You can see resistance drops rapidly with the increase in the voltage as above the rated voltage. You see resistance decreases as the voltage increases through this graph. Now this is the characteristics graph of the varistors. Right hand side we are having the forward region, and left hand side we are having the reverse region. Forward region, by applying the forward voltage and the variable voltage, there you see the varistor work IV curves, and then left hand side, and this is a symbol, left hand side you are having the symbol which represent the varistor, forward current and the reverse, how it works in the forward and the reverse biasing. So we can see that the varistors have the symmetrical bidirectional characteristics. Varistor operates in both the direction. Quadrant 1 and 3 we can see sinusoidal waveforms behaving in similar way to the Zener diode connected back to back. It works in the forward and the reverse bias, which is a practically rated voltage. When not conducting, IV curves show a linear relationship as the current flowing through the varistor remains constant and low at only a few microampere of the leakage current. After this, due to its high resistance acting as an open circuit and remains constant until the voltage across the varistor. Then this rated or clamping voltage is the voltage across the varistor measured with the specified DC current of the 1 milliampere, and this is the DC voltage level applied across its terminal that allows a current of 1 milliampere to flow through the varistor's resistive body, and which itself depend on the material used in its construction. It means the varistor is flow of voltage depend upon also the material which we are using. At this voltage level, the varistor begins to change from its insulating state into its conducting state. Means we are supplying a voltage to change the varistor from insulating to the conducting state. When the transient voltage across the varistor is equal or greater than that of the rated value, the resistance of the device suddenly becomes very small, turning the varistor into a conductor due to the avalanche effect of its semiconductor material. So it depends upon the material also. The small leakage current flowing through the varistor rapidly rises, but the voltage across it limited to a level just above the varistor voltage. So, on the other hand, the varistor self-regulated the transient voltage across it. How it self-regulated? It allows the more current to flow through it, and because of its steep non-linear IV curve, it can pass widely varying current over a narrow voltage range, clipping off any voltage strike. So, the most important type of varistor are the metal oxide varistor, that is known as the MOV, which is a non-linear transient suppressor composed of zinc oxide. Metal oxide we can use any type of. Another type of varistors are the silicon carbide varistor, At the one time, this was the most common type of the varistor before MOV comes into the market, and these components utilizes the silicon carbide, as the name suggests, silicon carbide varistor, that is represented by the SiC, and they are known as the intensive use for the high power, high voltage applications. But the disadvantages of this type of varistor, that it draws significantly standby current. They can draw the significant standby current. Therefore, a series gap is required to limit the standby power consumption. So, these are very simple in the shape. Alternate type of the surge suppressing devices include, we can have many, like the selenium cells, and these suppressors are selenium rectifiers allowing a high energy reverse breakdown current. Some selenium cells have self-heated properties and allow them to withstand high energy discharges, and however clamping ability of the modern MOV. Next type is the Zener diode, as commonly we use. A transient suppression devices and utilizes the silicon rectifier technology, and they have a very constant clamping voltage. The major drawback of the Zener diode is that they have a limited energy dissipation capability. Next is crowbar devices. A crowbar device is a short circuit, a surge to ground. This short circuit will continue until the current is below a certain very low level, that creating a lagging or power flow effect. For example, crowbar devices, we have the gas discharge tube, thyristor surge protection devices, and these type of devices used in the crowbar devices. In the gas discharge tube or the spark gap, these devices conduct after conducting the spark is created, and disadvantages for this type of devices is take a relative long time to trigger. Advantages of this, the large current carrying capabilities, having this type of tubes, this type of spark gap. Thyristor surge protection devices and have the similar characteristics as to GDP, but can work much faster than that of the GDT. Next type of that is most commonly used varistor are the metal oxide. Metal oxide, where we use the different type of metals for its construction. Different type of metal oxide pressed into a ceramic like material, and sometimes we can have a zinc and other materials we can have, and this metal varistor consists of approximately 90% of the metal oxide as a ceramic, and it is coated on the ceramic based material, and plus other filter materials for formation of the junction between the zinc oxide gain. Metal oxide varistors can now the most common type of the voltage clamping devices and available for the use of the wide range of the voltage and current. And this use of the metallic oxide within its construction means that MOV, metal oxide varistor, are extremely effective in absorbing the short term voltage transient and have the high energy handling capability. It means when we are using for devices which is having a high energy, then we use this type of the metal oxide. As with the normal varistors, the metal oxide varistors starts conduction at a specific voltage and stop conduction when the voltage fall below a threshold voltage. So, a value is fixed up to the threshold voltage, where it stop conduction when the voltage is up to the threshold voltage. The main difference between the standard silicon carbide and the MOV type of varistor is that the leakage current through the MOV metal oxide is very small current at in normal operating conditions, and its speed of the operation in the clamping transients is much faster. So, these are the basic difference. Moreover, the MOV metal oxide varistors generally have radial leads and had the outer blue or the black epoxy coating when closely resembles with the disc ceramic capacitors and can be physically mounted on the circuit board. And PCB, as a similar manner, we use this MOV, that is a very small component, and this construction is typically metal oxide varistor is here we define. You see here that this type of the metal oxide which is having a two terminal is put on the PCB. You see we are having a two wire connecting lead and current flow in between that, and metallic electrode are there, and it is on the ceramic on the zinc oxide. You see zinc oxide put on this ceramic, and epoxy is there, and here we are having a metallic electrodes on both the side which is used in the connection, and this is the ceramic layer on the zinc oxide. Now, to select the correct MOV for a particular application, it is desirable to have the some knowledge of the source impedance and the possible pulse power of the transient for incoming line or the phase bond transient. So, selection of the MOV is little more difficult as generally the characteristics of the power supply are known. There are many factors on which the selection of the metal oxide varistor are used. In general, MOV selection for electrical protection of the circuit from the power supply transient and spikes, it is often little more than that of the educated guess. However, metal oxide varistors are available in a wide range of the varistor voltage from 10 voltage to the 1000 voltage for the AC or the DC. So, selection can be helped by knowing the supply voltage where we use this varistor. For example, if we select the MOV or the silicon varistor, for that matter the voltage, its maximum continuous RMS voltage rating should be just above the highest expected supply voltage. It must be 130 volts RMS for the 120 volt supply and 260 volts RMS for the 230 volt supply. So, maximum surge current value that varistors will take depend on the transient pulse width and the number of the pulse repetitions. Assumptions can be made upon a width of the transient pulse which are typically 20 to 50 microsecond long. If the peak pulse current rating is insufficient, then the varistor may overheat or become damaged. So, the varistor to operate without any failure or the degradation, it must be able to quickly dissipate the absorbed energy of the transient pulse and return safely to its pre-pulse condition. What are the application of the varistor? And they are used in the protector devices. Source of high voltage transients can include the lightning strikes, electrostatic discharge, inductive discharge from the motors or the transformer. Varistor are often used as a surge protector power strips. Special type of the low capacitance protect communication lines. They are also useful for the wide application where we can include in the telephone and the other communication line protection, radio communication equipment transient suppression, surge protector power strips, cable TV, power supply protection, microprocessor protection, electronic equipment protection, low voltage board level protection, transient voltage surge suppressor, car electronic protection, industrial high energy protection. So, these are the basic application of the varistor. Thank you very much.